Okay, so let's go and get started. Good morning, everyone, and thank you for coming for this pre-seminar. I'm going to introduce our speaker who is coming from from Northwestern University. So Hoang completed his bachelor's degree in civil engineering at Ho Chi Minh City University of Technology in Vietnam. And then afterward, he earned his master's degree here in town at Northwestern in 2017, so pretty recently. And since then, he's been gently advised by Professor Bujan and Professor Espinosa to pursue a degree still in TEM, so he really remains in TEM. He's interested in multi-physics and multi-scale phenomena in rock-like materials, primarily concrete, and how to apply his understanding of those phenomena into sustaining structural serviceability and improving other human structure interaction activities. And aside from research, well, he enjoys reading natural and hard science books and jamming mashup from random songs. So today is going to talk to us on effect of parallel compression or tension on structural scaling strength of material as applied to concrete, composite, and metal. So Hoang, we are all yours.
Thank you, Professor Akono, for your kind introduction. I will share my screen now. Yeah, everyone can see it, right? Yeah, thank you. Yeah, so as Professor Akono mentioned, so I worked for a while in the topic of find out how the crack parallel compression or tension on the structural scaling strength of the materials. And today I will introduce you such an effect of crack parallel stress on several materials, mostly categorized as quasibrittle material and ductile material. And some of them can be listed as concrete, composite, and aluminum alloy. So hopefully at the end of the talk, I will get you a little bit more interested in fracture mechanics and its magical word. Yeah. So to start with, fracture mechanics start to grow or originate from some of the unfortunate incident during World War II, where some ships accidentally fell. However, the design strength is still satisfied the requirement, but it still failed, and the strength at that level they felt were lower than they expected. And then Griffith started a fracture mechanics study and comes to the definition of fracture mechanics is a failure theory that determines when and how the material fail based on the energy criteria, not on the strength criteria. And the failure can be propagating throughout the structure rather than simultaneously or immediately entire failure zone or surface. And when I searching for some of the illustration for the mode of fracture, I came up with some interesting illustration from Charles Ennis website. So these pictures show the mode of fracture, and some of you may know that there are three modes: the opening one, the in-plane shear one, and the outer plane shear one. And in this talk, I will focus on the opening mode. So for the opening mode, to extract the fracture behavior, there were some multiple test configurations. You can use the single edge notch bend test, which are similar to 3-point bending test, or you can use the same type of specimen, but you put this specimen in tension. Another type is a sharply notched cylindrical tension and double cantilever beam. So in some of the extended creep experiment, people can use double edge notch, and a lot of composite testing involved the compact tension. And checks in 1985, around 1985, came up with wedge splitting tests, which are another a way to create a tension ahead of the crack tip and trigger the opening mode. However, the fracture is way more complicated than that. So what draw us into this direction is the shear failure of the reinforced concrete beam. So so there were some experiments have done in this type of beam and this type of loading configuration. However, when we try to use the cohesive zone model and an LEFM based type of model where the crack is aligned, we cannot capture the Vmax that reflected in the measurements. So when we looked into the problem more carefully, we realized that the shear fracture of beams on slab must include a larger tensorial fracture versus zone rather than a crack being aligned. So the interactions of this zone, and as you can see from the illustration here, similar to the strut and tie model people usually use in ACI, when you subject to a shear crack and there was like a compressive line forming between the support and the applied the loading point. And because of that high compression, there will be interactions between the compression that's just created and the opening mode caused by the failing load. So from that mismatch, we think there should be some interaction there, and that makes the Vmax cannot that caused the LEFM and cohesive crack model couldn't be captured, could not capture the Vmax here. Some situations is similar, for example, in hydraulic fracture, especially in when we couple the paramechanical stress transfer to solid, when you have the water come into the crack and fracture the internal band of the crack. So when under the intact condition, the rock and other type of the rocks and its surrounding environment is quite in the hydrostatic stress or very close to hydrostatic stress. However, when there's a crack, there's some release of the transversal stress and it creates the deviatoric condition. And under this condition, the breakdown pressure has been observed to be either higher or lower than it should be. So that also can be a scenarios where the crack parallel stress come into effect. And another scenarios coming from the biomedical case when you have the failure of bovine femur or the femur in general. Because femur, as you can see, that it's constantly subjected to the compressive load. However, when people get older, there's a change in the body condition. There's some osmotic and maybe some drying out of the bone tissue. So those gradients are changing, causing some crack to form, and the compressive stress, which the bond is always subjected to, will cause it to be easier to fail. So why crack parallel stress? We see why crack parallel stresses matter. Now we see how. So imagine a thought experiment where you have a block and we have a crack, and the block subjected to several crack parallel stress, sigma ZZ, sigma XX, sigma ZZ, and sigma XZ. In the cohesive crack model or LEFM based model, you have only the lie crack, and any existence of the parallel stress will not cause any change in the stress field. And this is only be true when you have a very sharp cleavage that go through or cut through the atomic bond. And this strictly applies to the nanoscale only when you have like two sides of the crack being separated, or two sides of the atoms are separated. However, in reality, the damage or like more mechanisms can happen. Like you have a damage zone or fracture force zone, and from now I will refer it to be FPZ. Such a zone can appear on the crack, and when you have a crack parallel stress, it has an interaction with such a crack parallel stress, and will either and will have a certain effect to the fracture energy. And in another scenarios, when you have, for example, in metal, you have a polycrystal or grand batteries forming, depends on how and what is temperature you create or you fabricate the metal structure. It can also come to interact with the crack parallel stress and causing some deviation from the conventional theory. And in this case, we may see some change in the GF, which is the fracture energy, and such a it can cause a deviation from the surface energy, pure surface energy. However, in the current experimental configurations, people don't really care or don't really, first of all, they don't really pay attention to the crack parallel stress. So that's why on of these proposed experimental configuration do not account for such a stress. And the aim of my study is to come up with a configuration that we can measure the effect of such a stress, and then using the numerical model to understand what is happening within or when you have the structure that's subject to crack parallel stress. So now I would mention about the distinction between the fracture theories. So since Griffith in 1921, the fracture mechanics has evolved into several branches. And the main branches can be listed as cohesive crack, ductile or elastoplastic fracture mechanics, or quasibrittle fracture mechanics. And the difference between them were that in brittle mechanics, you consider the entire domain to be linear elastic, and any nonlinear or inelasticity will be limited and can be simplified into a point. However, in ductile material, surrounding that point and the linear elastic domain, there arise a nonlinear hardening. So the nonlinear hardening comes from the plasticity of the material, and it also can affect how it interacts with the crack parallel stress. In quasibrittle material, that's another story. Instead of a ductile or nonlinear hardening region, you have a softening region, which is painted black here. And in this case, you have a finite domain of softening, and hence it also can suggest a change in the GF if you have an interaction with the crack parallel stress. So first I will talk about a quasibrittle material. And what makes a material quasibrittle? So it should have brittle constituents, which is the matrix that matrix and the inclusion that having the themselves are brittle materials. No plasticity, or strictly strictly speaking, there will be some plasticity, but like the effect will be negligible. And also the intertwine between the materials will be created in a way that the inhomogeneity size would cannot be neglected. And some examples of the brittle quasi-brittle materials are concrete, which I tackled here, and others are top ceramics, and some notable mention should be biological shale and gas shells, and brittle materials on the micro and nano scales. Because as I mentioned, strictly speaking, at the micro and nano scales, many of the materials become the heterogeneity will arise. And you can see a simple illustration here when you have a transition from the ductile to quasi-brittle and to brittle materials when the size becomes bigger. So for the fracture, for the quasi-brittle materials, one notable feature is the fracture process zone. It is the area or the domain where the heterogeneity takes effect. And for example, for Arctic Ocean ice, it can span over 10 kilometers. For sea ice, it can be 5 meters, and for normal concrete, because of the variation in the aggregate, it can span from 5 to 50 centimeters. And for others like textile composite, it can be smaller and smaller when you consider the materials at a smaller scale. And here I want to emphasize that quasi-brittleness is a relative concept, because heterogeneity, and it should depend on at which scale the heterogeneity will arise. So we know some of the something about the quasi-brittle material. So how to apply the crack plateau stress and see its effect. So we came up with the new loading configuration which is called gap test. This is a simple and also an unambiguous way to extract the effect of the crack plateau stress. So several features can be listed here. So you have a specimen, a single edge notch specimen subjected to like 4-point bending, but it's not quite right, because 4-point bending, in the 4-point bending test, you have a 3 equal span length. This one, the load is applied in at 2 points here at a separated distance. At the beginning, the specimen sit on a yielding pad, and this yielding pad is made of a plastic material, and the requirement I will mention later. So after the load is applied, the pad will deform elastically and then plastically at the end, and then it will go, but it will not be subjected to any bending moment, because there was a gap here. However, after a while, the gap will close while the crack plateau stress from the pad still applied, and the bending moment that can trigger the crack start to apply here at the support. And later, both at the crack tip, it will subject to both tension for the crack and also compression from the crack plateau stress here. So the beam is hypothetically transformed from one statically determinate system to another statically determinate system. And because of the constancy of the crack plateau stress, we can use it along with the size effect method, which I will mention later, to extract the fracture energy. So a more detail of the schematic setup is shown here when you have some steel pad, and there's some technical requirement here when you don't allow the rotation and the slip when it comes to the experimental configurations. And also for the plastic pad, because of no rotation here, we can conserve the symmetry, which means the equal deformation on the plastic pads. And as I mentioned previously, that there's one requirement for the plastic pad. The plastic pad is supposed to give the constant pressure or constant crack plateau stress here. So it should be made from a material that can produce such a behavior. So here for concrete, I found a material which is called polypropylene that has a very clean and very good yield plateau, where the rise of the plateau is around like 0.39% when the when the moment start to apply. And you can change the crack plateau stress, the level of crack plateau stress, by changing the material to other materials that can have similar behaviors, and or you can detail or design the cross section of this material to modify the crack pillar stress that you want. And this is the a realistic test setup. And here you can see that it reflects exactly what I just showed in the scheme. And one loading process will start with the increase of the load from the elastic of the plastic elastic deformation of the plastic pad. And then after a while, it touched the support, the side support, and the moment to trigger the opening mode of fracture will causing another rise. So the requirement here is that you have to leave the gap so that the fully plastic strand is developed within the pad. And you can confirm that by after the specimen broken up, you see the drop back to the plateau, plateau here. And when I did the experiment, I put an extensometer because this is the most exact way to measure the deformation on the experiment rather than the machine displacement, which can cause a mismatch because machine has some stiffness, right? And extracting those information from the specimen here, you can read the load and crack tip opening displacement and can gain some understanding about how the fracture developed and the fracture energy within this material. So I use a numerical code to confirm the uniformity of the stress field under the subjected to the crack pillar stress here. And you can see that the stress field is quite uniform, especially near the crack tip, even when you reach the maximum moment when the crack start to grow. So this is very important because if you use, for example, too narrow pad, the stress field cannot be as uniform because you can see at the edge there's some like a bulging area of the stress, and then the stress constant measure at the tip will not be reflected exactly by the stress at the plastic pad here. And also there's some caveat here because you can see there's a crack, so the stress measured from the pad, which are also measured from the machine, is not exactly the stress here at the tip. So to visualize the stress, the real sigma x at the tip, we use a numerical model for that. And the elastic, we found that the elastic model can give a quite accurate approximation of the real model with the damage. So the elastic solution can also suffice. It's worth mentioning that there were some attempts for the similar idea. However, for checks in 1995, he developed some of early idea of the test in 1990, and then finalized and perfect the design using the wedge splitting along with the second fixture to apply the crack pillar stress on the wedge splitting specimen. However, in this case, you can see that is a work of fracture method. It means that it requires full measurement of the load displacement curve of the crack or load crack opening displacement curve, and no size effect were tested. And I will mention about size effect later and how it matters. However, one big caveat of this test is that you have non-uniform stress field or non-uniform crack pillar stress field, because when you apply the opening mode here, a certain part of the applied load goes into the vertical component, and that vertical component transfer into the specimen, and then you have non-uniformity in the stress field. So one key point of the gap test is the design and how to apply the crack pillar stress onto the specimen. Another is the size effect method. So the size effect method is a method to measure the fracture energy of the materials. And this fracture energy corresponding to the original, the initial part of the cohesive law for one material point. So for example, if you use a cohesive model and you measure and you implement the bilinear curve for the bilinear curve for the cohesive layers, the size effect will calculate or will give you the energy of the initial part only. And this is the most important part, because the later part will happen when you have a very big separation and the material should allow a very big opening. And at that stage, the load measure is far in the tail already. And that's such of information is important only when you consider the ballistic or the resistance to the impact of the material. But most of the case in quasi-static structure, the G small f is what matters. And however, the G capital F can be calculated from the certain ratio of G capital F over GF separately, once you know the G small f. And another caveat of the G capital F is whether or not the tail of the curve is unique. So for example, in the case when you have a 3-point bending specimen here, when the FPZ start to grow and propagate through the specimen, at the end, you have the battery effect here, right? So the entire FPZ will be changing at the end, and what you measure here may not be exactly what the material properties should be. And that leads to change or variation in the J integrals with the crack length, and as a result, an ambiguous reading of the fracture energy. So how to do the size effect method? So the size effect method is based on the basic assumption that the FPZ of the material is a constant, has a constant area or constant volume. And when you scale the specimen to a bigger size, that domain, that area of volume does not change. So you can break the energy of the materials into the part that it will be released, and what will change with the size, which is the elastic part starting here, and then the energy that dissipated within this zone. And that you can see that does not depend on D. And after manipulating the to get the sigma n, which is the nominal strength, and in most cases it's just defined by the maximum load that you can measure over the thickness and the characteristic length, you can obtain the relation between the nominal strength and the size of the material. I'm sorry, size of the structure you measure. And this can be turned into the linear regression curve. And this, by fitting these, we can extract GF and CF, which is the characteristic length of the materials. So the size effect here, you can see if we expand the size effect curve in the regime near 0 dimensions, we can have here some of the the asymptotes when you have a 0D. And if you expand that in with the big D, then you have another asymptote with infinitely large specimens. Oops. Also, this is the asymptotic matching uses size effect law, and it can be seen here. I'm sorry, do you see my panel? Because I keep moving them around. I'm not sure if the audience see the same thing as mine, as I am.
You can see it, Zdeněk.
Oh, okay. Let me share this slide only. Yeah, I think this one will be less disturbing. All right, so now we incorporate the gap test and the size effect test method to get the fracture energy and to see how the crack parallel stress affects the fracture energy here. And you can see that we scale the entire setup, and we keep the aspect ratio the same, and also the thickness, outer plane thickness, the same. So the result from the gap test can be showed here, and it follow quite reasonably with the size effect method. And from these, we can extract the GF and the CF, as I mentioned before. So here's the result of the GF when there's a presence of the sigma XX here, and we see a non-monotonic trend. At the medium intermediate level of the sigma XX, you see an increase in the GF. However, when there's a higher sigma XX close to the compressive strength of the materials, you will see the lower or the degrees of the GF, and this result suggests a strong dependence of the GF on the critical stress sigma XX. So how to explain those mechanisms and like the relevant behaviors? So we used a model called microplane constitutive law model, and it was trained within our group, and the model is based on the breaking of the breaking of stress strain tensor into the stress strain vector onto many or multiple microplanes. And this is reflecting the fact that in the quasibrittle material, heterogeneity will also appears, though stress and strain vector appears on the surface of the heterogeneity. And this model can capture several behavior, and especially in the triaxial state, stress state that appears at the crack tip is tensile cracking, splitting or the spreading of the micro crack, and also the frictional, the latency. And this constitutive laws use the relation between the stress and strain vectors and to model the behaviors, and then turn the stress vectors to the stress tensor by the variational principle. And so within this framework, so at least 21 microplane normals are required to get a certain level of accuracy. However, in this study, we used 37. And the basic algorithm is presented here when you start with the macro strain tensor, and then you use the kinematic constraint to turn them into micro strands. And those micro strands include the normal and the components of the normal, which are the volumetric and deviatoric, and then the shear components on each plane. And the constitutive, microplane constitutive law gives you the relation to those strands to the corresponding micro stresses. And then the principle of virtual work will help to turn the micro stresses vector into the macro stress tensor. And the important one cool case about the microplane model that can simulate is the vertex effect. So the vertex effect is the path material, the loading path, where you have the first compress the cylinder and then do a torsion to it. And the plasticity-based model will predict constant stiffness of this effect, of this loading scenario. However, in reality, in experiment, they show a decrease. So by
Hoang, can I interrupt you to say you get some
sure.
strange behavior in the chat, which we need to do something about. Should we just remove this person, Angie? I mean, I don't know who this is.
Yeah, I saw some pop-ups.
I think we should remove them, yeah.
Okay, I don't know who Mirage. I have the ability to do it.
I don't know what it is.
Yeah, so
Yeah.
sorry for the distraction there. Keep going. Well, I guess, Angie, let's keep an eye on whoever that is and kick them out again.
Okay.
Okay, go ahead, Hoang. Sorry.
Right.
Sorry to everybody for that very distracting series of bizarre chats that were appearing there. This is my first experience with I think that's Zoom bombing, right?
Yeah, zoom
I
bombing.
think we got, but I don't know how we got zoom bombing. It's supposed to be only,
Yeah.
Not
that should be
Western.
Okay, so sorry, Hoang. We'll keep an eye on it for you. Sorry about that.
It's not a national secret, so hopefully it's not leaked anywhere.
All right. Right. And they're not chatting
Uh,
anything too offensive. It's just bizarre. It's
yeah.
distracting. Go ahead.
I think they've left.
Yeah.
Yeah.
Well, I removed them and hopefully they don't come back. Yeah.
Okay.
So I continue for that. So the microplane model is basically tuned or parameterized to fit several phenomena in concrete, and it covers quite a wide range of phenomena in concrete. And herein we inherited some of those parameters and just changed the one that we need to fit our demand. And in this case, we tuned the free parameters to fit the uniaxial compressive strength of the material of the concrete, because it directly related to how the compressive stress that apply into the specimens. And another is the basic fracture energy, which is the same test, but when you don't apply any of the pad. So at that case, you have a sigma xx equal to 0, and you have like a baseline of the fracture energy GF0. And from the fitting fitting results here, we can conclude that it gives a decent fitting, and then we can definitely use sigma xx for to predict the behaviors of the materials when sigma xx is non-zero. And here are the results, and you can see that the curve of the microplane model prediction follow the same trend, and at some point it fit very well the material experimental result. So by normalizing the curve and the entire data using the GF0, the baseline fracture energy here, we can see that we underestimate a little bit at the M7, I'm sorry, at the intermediate stress level here. But we capture correctly the behavior at the very high stress. And also we see, observe again the non-monotonic trend when sigma xx increase. And here one note I want you to pay attention is to change the two different curves. Because I mentioned earlier that the sigma pad or the applied stress is not exactly at the stress level at the crack tip, so we have to change it, or we have to extract the information from the microplane model at the elements at the tip to get the sigma xx at that level. And also the same trend shows here when you compare the characteristic length of materials at the different sigma xx. And if we assume that CF, the characteristic size 40%, characteristic length 40% of the Irwin's length, then we can calculate the Irwin's length and also apply it to a cohesive simulation. So what were the mechanisms that lead into that non-monotonic trend? So we hypothesized that at the intermediate stress level, there's a strengthening behavior. The strengthening comes from the high normal stress or high compressive normal stress level that increase the friction and interlock of the small and the large aggregate within the concrete. And when you comes to separate the materials by the bending moment, those interlock and friction will increase the strength of and increase the resistance against opening mode. However, when you increase the stress more to close to the compressive strength of concrete, there will be slip and splitting bands forming at the crack tip. And because of this slip and the splitting band, it expands the volume of the material at the crack tip, and then it will causing the drop in the fracture energy. However, the width of the fracture energy, the width of the fracture process zone will be widened. And I just show you, this one is just eyeballing kind of picture. And right now we invite the collaboration from advanced, the group that have some advanced image technique that proving the hypothesis that we propose here. So we see the effect of sigma xx, which is pronounced in the fracture energy of the material. So how about outer plane crack parallel stress? So here we have done some prediction using the outer plane crack parallel stress sigma zz, and we can also observe a non-monotonic trend when we apply the sigma zz. And the strongest case in which the material can be it cause the biggest resistance is when both sigma zz and sigma xx is in their intermediate range. It means that you attain the peak of friction and interlock of the aggregates within the materials. So, okay, now we see that the GF is depends on sigma xx, and with the any cohesive lie and crack model and LEFM based model, it cannot be used if such a phenomenon is simulated, right? So then a GF we can so we can still use a cohesive zone model or lie crack model when with the GF modify is a function of sigma xx, and then from the shape of the curve, we propose a form of the functions of such a dependence here. So it's good, right? Not quite, because the relation, such a relation I mentioned, is the loading path dependence. So it is path dependent in a way that when you apply the crack parallel stress field in the gap is in the case of the gap test, right? And then you have you apply the fracture or the bending moment to create fracture. It will result in a different GF from the case when you apply the moment first and then apply the compressive crack parallel stress here. So then it negates the purpose of the GF as a function of sigma xx, and then it requires it calls for using the correct model whenever you have to deal with the similar scenarios. So another source of confirmation comes from the J integral. So we use the J integral together with the microplane model, and because in this is the continuum model, so we have to turn the J integral, which is the lie integral, contour integral, into something that we can measure from the M elements, and that can be extracted conveniently from the finite element. So Zhang, Shi, and Needleman offer such a method, and we can this relation can be derived using the Green's theorem, and then after that we can extract the information from the J integral here and the peak load. And I use two contour here, and you can see that from the relation and also from the magnitude of the increasing contour 2 it agrees better with whatever we measure from the GF. And here you can see that because of the contour 1 is too close to the crack, and one hypothesis of the J integral is that it should not cross any unloading area or unloading volume. Hence, the contour 1 is still the unconverged value of the J integral. So that's something that we should keep in mind. So we have some hypotheses about the FPZ changing with the sigma xx. So by varying this contour 1 in certain or in some cases that this start to converge to contour 2, then we can kind of know the extent of the FPZ within the crack. So when I did that, I can extract some of the change in the shape of the sigma of the fracture force zone, because here the rectangular domain is the most convenient way to simulate the contour and also the corresponding domains to that contour. So I can see some change like in a relative way about when you see when you have an intermediate stress level of sigma xx, there's an increase in the CF here, but it's not increase in the lateral side. But when you have a higher stress sigma xx, you have an expanding but a shorter CF here, which somehow reflected our hypothesis. But again, it is just a very rough estimation, and it counts for more advanced image technique. So another point we should note is if you use the tau, the Morse circle to kind of plot the stress trend, the stress level, the stress state at the crack tip. And if we denote the tau is the difference between sigma 1 and sigma 3, which is the stress that causing the fracture to occur, and then the sigma and the crack parallel stress, you can see that there's no envelope exits here when we zoom in the image here. And also another note on the type of the model can simulate this phenomenon. So Drucker-Prager is one of the case that we have failed to produce such a result, and you can see that it produced a wrong trend here. And we also examined the CDPM2, which is the tensorial model of the concrete, and you can see that because it captures some traxial traxial stress state behaviors, so it can follow the trend of the data point, but not the value. So knowing the result for the concrete, we are attempting to do some prediction for the fiber reinforced concrete. And for fiber reinforced concrete, as we know that it has a higher fracture energy or higher baseline fracture energy here. So when you apply the sigma, when the concrete has a fiber, it's had a bridging effect. That resists the crack to open and lead to the higher fracture energy. However, the trend is kind of similar. And another note is that it has a more gradual drop when the sigma xx comes close to the sigma c. And another extrapolations we have done is for shale, and the fracture energy for shale in the case that you have the bedding plane perpendicular to the crack, it follows strictly the trend in the concrete. However, when you have the bedding plane parallels to the crack, because it is very sensitive to the splitting, because you have the weaker plane that is already aligned with the crack, the strengthening regime is very limited, and you can see that it's more sensitive to the sigma xx. However, it's not usually the case in fracking, because in fracking you have the crack that expand perpendicular to whatever the embedding plane is based on the natural stress state of the rock. The final prediction for the quasibrittle material is for composite. So we applied also the same configuration, testing configuration for composite, and applied it to a certain 60% of the compressive strength of a composite, and we can see an increase of 48%. And this composite, I want to have a note that this composite is a quasi-isotropic type of composite, which means that you have the fibers run in all directions, and in this case they run in 0, 90, 45 and minus 45 degree. So that is the fracture of the quasibrittle material, and we see very strong effect of the sigma xx on the GF. So how about the more ductile materials like metal? In this case, the story is a bit different. So in metal, instead of a very big large fracture zone, we have instead the yielding zone here. And the yielding zone, as I mentioned at the beginning, that it is the zone or the volume that materials become hardening. And in large scale yielding, the zone, such a zone can cover the very large part of the specimen of the structure. However, when the structure becomes bigger and bigger, that ratio will become smaller, and you have the yielding zone is completely contained within the specimen. And this difference counts for another theory to scale the structural strength to extract the GF. And here we hypothesized three types of asymptotic domains. The first one would be the FPZ scale, which is the micron scale. So the heterogeneity size of the metal is quite different from the concrete or other quasibrittle material, is that those depends on the grain scales or the grain boundary, where the grains with different crystalline orientation arranged differently, and they separated by the boundaries. Also, you have the rise of the intermediate regime when you have the large scale yielding. And when the specimen becomes bigger and bigger, this yielding zone will be very small compared with the entire structural size, and then it converges to the LEFM theory. So it's worth noting that there were some picture about the scaling of picture about the specimen with different scales using for metal. However, such a size effect has not been attempted or has not been measured, and also these only serve to investigate the fatigue strength, and those are tested at the Westinghouse, and we received those from one of the reviewers of our papers. So how to come up with the correct theory for the scaling of the ductile materials here? So first of all, we used take advantage of the HRR theory. That was the abbreviation of the name of the founders, which are Hutchinson, Rice, and Rosengren. And this, based on using the deformation theory of plasticity, means that they use the total strand as the plastic strand theory, and this strand is presumably follow the nonlinear elastic regime, which in that case you don't have any unloading happening at the yielding zone or the HRR field. And the Rambert-Osgood law assume that the strain is a power law of the stress, and then hence it results in the corresponding power of the strain and the stress here. So using the for large scale yieldings, which means that you have the specimen size that are comparable to the yielding zone, you can come up with some power of the strain field and the displacement field. And you can see that the stress field should follow the power of -1 over n+1. And because of the relation from Rambert-Osgood law, you have the strain follows the power of -n to the divided by n+1. And then the displacement field is the integral of the strain field here. So hence it follows 1 over n+1 field. So to scale it correctly, we instead of using a very complicated shape of the Ewing zone here, we condense it into a single size, a single characteristic size that can represent the Ewing zone. So we hypothetically assume that it is a circle, and then it can be changed. I'm sorry, it can be the radius of the circle can represent the entire Ewing zone. I'm noticing that I'm kind of running out of time, so I'm trying to going faster. You can post the questions after from me. So basically, we can use the virtual works of singular stress field and uniform strain variations. We can come up with the calculation for such an RP, and then we just use the same strategy, which is that breaking the energy to the term that depends on size and the terms that doesn't depend on size here to scale the materials. However, the caveat of that assumption is that we should use always the case or the scaling of the structures that completely contain the Ewing zone. And that, so the energy will come from the part here when you have the release of the elastic band of the materials, and the release of when you have the moving up the wake of the plastic zone. And also from the material point of view, the energy will be broken up into two parts, the plastic part and also the part with issue in which the come from the fracture process zone, which is a micron in scale here. And so that the assumption that I just mentioned is applied for small scale Ewing when you have the structural scale or structure that has a size bigger than the domain size, I'm sorry, the Ewing zone size. And that ends up with a similar formulation for the scaling or the size effect formulation. However, the relevant terms are different from the quasibrittle materials, and that should be, some of the details should be read in using the non-dimensional integral over the HRR field, which take into account the shape of the field. So now we have the log size asymptotic, which the entire structural size cover the entire process zone. I'm sorry, cover entire Ewing zone. So we have to replace such a RP or constancy of the Ewing zone by a zone that changing with also with D. And the way that it changes with D comes from the RHRR field solution. And hence we have the transition formulation here, which we can cover in the entire domain of D. And Dr. Abdullah Donmez, who is in Turkey now, helped us run the test on aluminum for the size effect. And it is specifically detailed for aluminum alloy 6061 T651. And the result shows that such a law can be applied. So either you assume that you have a small scale Ewing and then fitting the log size structure, or you have the large scale Ewing and transition Ewing also, large scale and small scale Ewing, and use the transitional formula to fit the GF. And such a GF follow quite converge to the J integral quite reasonably, and the difference is within 10%. So now it's time to see the effect of crack plate stress. And as I mentioned, it's different from the quasibrittle materials when you have the crack plate stress interact with the fracture process zone. Here it interact with the Ewing zone, and some previous study have been done. But for example, Cotterell and Rice has observed the crack path deflection due to the presence of T stress, but not the change in GF. So here we apply gap test protocol to the aluminum specimen. But as I mentioned, the plastic pad needs to be changed to match the maximum of the use strength of the aluminum. So we use copper, and for lower stress, we use the PVC pad. We can reach around 100 MPa. And we can see an increase in the fracture energy when we have a 15 increase in the sigma XX. And this change aside to the increase of the yielding zone when you have a larger sigma XX here. And from using like a plastic damage model by Professor Dr. Bai and Professor Wiebicki at MIT, we see some qualitative increase in the yielding zone size here, which reflects the fact that GF increase with the sigma XX. However, right now the quantitative result is not as promising, so we are doing some training the microplane model for such a behavior. In conclusions, the crack parallel stress should be considered when you have the fracture energy of the inelastic materials, and the same conclusions can be drawn for if the materials have any characteristic length that can interact with the triaxiality of the stress state at the tip. The scaling of the structural strand is an effective way to obtain the fracture characteristic or fracture behavior of the materials. And the computational model, in order in order to be effective, it should adequately describes the microscale mechanism. Similar so some example can be listed as LDPM by Professor Kusatis and microplane model by Professor Bajan here. And for quasibrittle material, the FPZ is the one that mainly interact with the sigma XX, and in the ductile material, the yielding zone is the one that play an important role. And at lower scale, the FPZ will start to manifest itself. And as I mentioned during the talk, that much more experimental verification is necessary to not only for other materials but also to image what we have been hypothesized as mechanism within the micro and meso scale happening at the crack tip. And I want to acknowledge my collaborators and the professor he's at Northwestern, and also Professor Issa at UIC that helped me during the research. And with that, I want to thank you for all of your attention, and I will take the question from here. Sorry, I'm a bit over time.
Okay, the floor is open for questions. Thank you for a nice talk.
Thank you for a second.
So I'm going to start with one question. Will you briefly describe the material that you use for your experiments?
So this is a planned concrete, and we order it from the Ozinga, and we target the Euro normal strength concrete, which is around like 30 psi in FC. So it's like a usual type of normal aggregate size, large and small aggregate size. Yeah, usual gravel.
By the way, we found it much better to order ready-mix concrete because it is far more homogeneous than we or anybody can do in the lab. In the tests of Hoover some years ago, he achieved coefficient variation of 2% with ready-mix concrete on 150 specimens. So we do have capable of mixing concrete, but we cannot do it as well. That's just a comment.
Yeah, and one of the thing is because the largest specimen here is 64 inches in span length, so it's also quite out of the reach in our mixing and also casting capability here at Northwestern.
Other questions? Okay, well, oh, go ahead, First Vision.
I asking, of course, many questions because we collaborate. But what do you see as the future direction of this study? I think that's a.
I mean, it opens a lot of possibilities because we are also targeting other materials, right? Like composite and shell. But it opens a quite interesting behavior in the stress state in the hydraulic fracture, because in hydraulic fracture, we see a change in the pore pressure when you have a penetration of the main crack. Then over time, such a stress state will cause maybe a favorable or maybe the adverse triaxial state. If there's some weakening regime in shell, then it will cause the close down of some main crack, and then you have either yielding a higher amount of gas, or maybe some crack will be inhibited. So I think it's very important in that scenario.
I fully agree. It's very different pore mechanics where you have gradual transfer from stress from fluid to solid.
Yeah, that's true.
And it changes also ratio of the stresses.
Yeah.
Okay, excellent. Well, thank you very much, Hoang. This was an excellent talk. And thank you everyone for staying until the end. And enjoy your Wednesday. Bye-bye.
Thank you, Professor Akono. Thank you, everyone.